Aloha and welcome, everybody. Friday, almost the weekend. Everyone know what Sunday is? Can't talk about church and state during class. Kidding. Yeah, it is. Have fun. Got a weekend off of coaching, so that's nice. Um, we ended last class talking about how much does the pH of a buffer change when an acid or base is added. Anyone remember how we calculate this? Jack? But so we the Henderson-Hasselbalch equation is the second part. So what was the first part? So it says here, calculating the new pH after addition of acid or base requires breaking the problem into two parts. One, we call the stoichiometry part. So what the heck? The first part is called the stoichiometry calculation. And if we add acid, so remember, we always have HA and A minus in solution, right? That's what we should review as a buffer. Just so everybody knows, all of these things we're applying with the weak acid and its conjugate base could also happen with a weak base and its conjugate acid. Okay? So if we were to take a weak base like ammonia, how do we know that's a weak base, Abby? Because it's not a strong base, right? So there's a KB associated with it. It means it does not fully protonate 100% to make a bunch of OH minus. Theoretically, think about what happens. So this is definitely a buffered system, right? If we add HCl, H plus, which is HCl, we can think of the Cl minus as a ion that just dissolves and doesn't react. What reacts with the added H plus to minimize the pH changes? Emma? The A minus, very good. The H plus will react with the A minus. So instead of just adding H plus, it reacts to make some HA. Adding HA will drop the pH a little bit, but not as much as if we just add the HCl. What happens if we add sodium hydroxide, which we can think of as just OH minus because the sodium plus is the counter ion? What reacts with this, Bryce? The HA reacts with the OH minus in this case. And basically the HA gives its H plus. So HA lets go of its H plus. So it makes the H plus. So let me use colors. The H plus here reacts with the green OH, the green OH minus to form water. But we generate a little bit of A minus. So adding the strong base is basically, in essence, adding the conjugate base, which is a weak base, and that will only have a very minimal pH change, increasing the pH. So that's how a weak acid conjugate base buffer works. Okay. Now, what happens if we were to add H plus to a base that consists of a weak base and its conjugate acid? Kayla, how will this NH3, NH4 plus respond to minimize the pH changes? In which it does not create more base. Huh? What reacts with the H plus? So does everybody see that this NH3 here is a weak base? It grabs this H plus to generate more NH4 plus, right? It makes the conjugate acid. Instead of straight adding H plus to a solution that would severely drop the pH, we're making that H plus into a conjugate base of a conjugate acid of a weak base, and therefore we have a minimal drop in pH, right? How would this buffer system here react with adding sodium hydroxide, which is basically OH minus? What do you think, Jessica? Nope. Angelina? So, I mean, when you add base, it does make it more basic, but how is it a buffered system? Any thoughts on this? Bailey? So we can just look and see the H plus reacted with one thing. The other thing is probably in there for the other thing, right? So what's the other thing that didn't react in the first part of the buffer? No, Kayla? So the NH4 plus has an extra proton, right? When the OH minus reacts with this NH4 plus, this OH minus grabs one of the extra H pluses. So NH4 plus, we can think of as NH3 and H plus combined to make NH4 plus. That is why it's a conjugate acid of the weak base. So it has that extra proton that's willing to be donated, which is the definition of an acid. And then what we see is this green OH minus here is like, oh, you're a conjugate acid. I'm going to take your proton to make water. Does water change the pH of the system? It does not. And now, so it's not all for nothing. It's not like it completely wipes it out. We still generate some increased NH3 when we pulled it off of the, so this was what that is, right? We pulled the H plus off of that, and now we make a little bit more of the weak base. Did we learn how to calculate the pH of a weak base? Yes, we did, using the kV and the same kind of fundamentals. So I don't have time to do every single problem 5 times to just like regurgitate it into you. That's why we have homework. That's why you practice the problems, okay? I show you at least one time, and you have to then go and take that and apply it on your own, okay? So the reason I give you homework is not because I am a person who loves making students have extra time doing work. It's because that's the only way you're going to learn how to do this is through repetition. When you get your driver's license, do they just say, oh, you passed this test, good job, you can now drive? Or what do they make you do? Take a driver's test, right? Anybody in here get their driver's license yet? You have to take a driver's test. But nowadays, when you're like 15 with your permit, I mean, when I grew up in Hawaii, you got your permit 2 weeks later, you could get your license. Yeah. And you also had so many hours of like driving time, right? So you had to practice. Is that because the DMV is like, let's waste a bunch of gas and pollute the environment? No, it's because you don't learn to drive until you practice it. You don't learn how to do these problems until you practice them over and over. Yes, Jessica. We're just adding. So in lab, did you add OH minus to a buffer? Was that, what do you mean a solution with something else? It was NaOH. So I wrote over here, OH minus comes from NaOH. So now I'm just saying, since I showed you the H plus we're adding comes from adding HCl, when I write H plus here, I'm implying that it was the HCl that we added. Over here, I said when we add NaOH, it gives us OH minus. So over here, I'm just saying we're adding OH minus, which is in the form of NaOH. So you're always going to add, you can never just add a minus and you can never add a plus. You always need to have a counter ion. We always choose counter ions that are what, Ida? Something from the end of chapter 15. Do we always add acidic counter ions, basic counter ions, or what would be the best one to add? Cade? No. Oh. Bryce? Neutral. Do we want to add a counter ion that's going to automatically increase or decrease the pH? How do we know what the neutral counter ions are? Have we learned that yet? How did we learn it? No, not from the periodic table. You have a list of strong acids and strong bases. Okay. So I take this class unbelievably slow and I repeat stuff over and over. I cannot just always be repeating and repeating and repeating. You have to take the time to think about stuff and learn from the stuff that I talk about, okay? This is not, let me give you every single answer and make sure you have it right. You have to actually learn. This is still college, believe it or not. I know COVID happened and everything is spoon-fed to us and everything's like, oh, let's just make it easy for everyone. But you have to do some thinking a little bit. And when I give a lecture, think about that and understand it, okay? I post videos for it. I do stuff like that. Let's try and retain some of the things that we are learning, okay? So that's how we do this. Now, if we want to calculate the pH change of a solution, let's go ahead and talk about what happens when we have, so we did this last time. Let's do an actual problem, okay? Do we remember this stoichiometry table from Wednesday? Were any of you here on Wednesday? Did anybody listen to the lecture on Wednesday? You should remember stuff that I taught you. I don't teach you stuff for one day and be like, cool, you learned it. Never remember that again. Weirdly, chemistry carries on. Are any of you planning on taking any other science classes in your life? Do you think that all of this stuff we're learning was just for one day and you never have to remember it? Or do you think that the reason why you have prerequisites is so that you can learn that stuff and then use it in later classes? What do you all think? You need to think about it, okay? And you all are some of the better students who actually show up, and I appreciate you for that. But you still have to take the time to think about what we're talking about and things like that. You cannot wait till the day before the exam to decide to start learning the material, or else you're going to have a very difficult time, okay? Now, they tell you, a little note, the easiest way to remember changes in relativity is relatively simple. Adding acid creates more acid. Adding base creates more base. So when I drew this crazy thing over here, when I added acid in H plus in the form of HCl, we added acid and the buffer reacts by converting its base into more acid. So when they say, remember that adding acid makes more acid, that also means you lose some of your base. If we add base over here, you see how when I said we add base in the form of NaOH, what happens? The acid goes down and you make more base. So adding base creates more base. Over on this side, adding base created more base. Adding acid created more acid. So do we see that? So this is the stoichiometry part of the problem. So let's go ahead and do this problem. Well, let's see where it is. Okay, so here's the problem. We have a buffer, well, we have 0.1 molar acetic acid, and we add 0.1 molar NaC2H3O2. What can we think of NaC2H3O2 as? Jackson, if you write that down, if you keep the Na, it might confuse you. What's a better way to think of it? So you get rid of the Na, but do we lose neutral Na or do we lose Na as an ion? So it's Na what? Plus, that means that so if this is Na plus, that must mean that this is C2H3O2 minus. Everybody see that? And basically what that tells us is we have 0.1 molar of the C2H3O2 minus, and we have 0.1 molar of the weak acid. Would this be considered a buffered system, Carissa? If you have weak acid and its conjugate base, is that a buffered system? Yes, it is. Everybody understand that? The same goes true for having a weak base and its conjugate acid by the exact same thing, just a little bit opposite, okay? I can't show you every single one. So when we have, so in this question, it says, they give us the Ka for the acetic acid. That's something that you can look up. It also says, since the initial amount of conjugate base and acid are equal, do we know the pH of this buffered system? What do you think, Ian? What is the pH of this buffered system? We may or may not have learned it on Wednesday. You may or may not have learned it in lab. You have lab today, right? So I don't expect you to maybe know it, but Natalie, do you have lab yet? So when you have equal concentrations of the weak acid and the and the conjugate base, what is the pH of that system?
The pKa.
Thank you very much. Someone on Zoom said the pKa. That's because we learned an equation, pH equals pKa plus the log of base over acid. If the base and the acid are equal, if it's 0.1 and 0.1, what does that equal? 0.1 divided by 0.1 is what, Rebecca? Huh? 0.1 divided by 0.1? 1. What if you had 7 molar and 7 molar? What is that ratio? What if it's a billion molar and a billion molar? What if it's 0.01 and 0.01? So every time these two things are equal, the log of 1, what does the log of 1 equal, Rebecca? That's maybe what you were thinking about. That equals 0. So the pH always equals the pKa when a solution, when a buffer solution has equal amounts of both. Everybody understand that? So that just helps us like start off with that tells us the pH of the buffer at the beginning. But now what they say is, so that's how they get that the pH is 4.74 to start. To find a new pH after 0.01 moles of solid NaOH are added, we're going to do a stoichiometry problem. So since they did this problem in 1 liter of buffer, and once again, I could make this really hard and I could put like half of a liter or I could put something else. But what is the definition of molarity, Nate? When I write a capital M, what does that mean? Over what? What's the units for molarity? Over what? Meters? Liters. Very good. So if I have a 0.1 molar solution, that means I have 0.1 moles per liter. If I'm in 1 liter, can we calculate how many moles we have? 0.1 moles, right? So that's why they say we originally have 0.1 moles of acid and 0.1 moles of base. Does everybody get that? Roughly. Yes? Okay. Now they're saying we add in 0.01 moles of strong base in the form of sodium hydroxide. Why do they say we're adding sodium hydroxide right here, but why do I only write in the OH minus, Jessica? Because that is the only part that matters. The Na plus is meaningless to us. They have to say it's there because you can't just add OH minus. It has to be counter-ioned. We always use sodium because that's the cheapest and easiest one, and it's pH neutral, okay? Now, if I'm adding base, what's that going to do, Robert? It is going to make more base. So how can it make more base? Very good. So the weak acid HC2H3O2 plus OH minus, the OH minus pulls off the proton of the weak acid. OH minus grabs out the H plus, so it pulls off an H plus, so that makes water. We don't give a crap about water in equilibrium because it is a liquid. So that doesn't get involved in the thing. But we can say of our 0.1 molar acetic acid that we started with, we lost 0.01 moles of that. That's where we get this 0.09 moles. Does everybody see that? But as Robert said, we added strong base and it makes, you see this? No, so did I draw that wrong? No, so we did that, right? The base reacts with the acid. What does that liberate? That liberates C2H3O2 minus. That is the base that Robert said we make more base of, okay? So we can say when we had 0.1 moles of this originally, we have to add 0.01 moles of this to that. That is where we see 0.11 moles, okay? That is the stoichiometry part of the problem. Figuring out which thing gets reacted and we lose some, and which thing gets created because the H came off of the weak acid to make some of the weak base, the conjugate base. Does everybody see that? Those are just the definitions of all of these things, okay? So now we know what our original things are. We can either do an ice table. Everybody remember how to do the ice table? We've only done it a lot. We make 0.09 minus x, x, and 0.1 plus x. We plug in all these values. Should we make x negligible? Only if we want it to be easy. If you want to do a lot of work, leave it unnegligible and see that you'll get the same answer anyway. Now what we see is we do all these steps, we double check, we get a pH of 4.83. Is there any easier way to do this, Cade? Instead of doing the ice table, is there some like shortcut formula that makes our life easy? Can we do the pH equals pKa plus the log of base over acid? pH equals pKa plus the log of base over acid. I thought that the pH always equals the pKa. Is that not true in this case, Kiana? Why not? Yes, Ella? Because the two concentrations became different when one of them got reacted and the other one got created. So when we have the same thing, we actually have to use the whole equation. Is this equation difficult to use? No, it's not. Here's the equation. To find the pKa, we take the negative log of the Ka. We take the log of 0.11 over 0.09, right? We plug that in. We get 4.83. Same value we got on the ice table. Everybody see that? What did we say was the original pH of the solution? 4.74. Sydney, does this make sense that a solution, a buffer solution that was 4.74 pH after addition of a strong base would have an increase in pH? Does that make sense? Why? Very good. So that makes sense, right? And Robert said when you add base, you make more base. But instead of adding strong base, which would severely increase the pH, we only mildly increase the pH because we're making weak base. Yes. Yes. So in this problem, that 1.8 times 10 to the negative 5 is given, but on the homework, the chapter 15 homework, that last page was a bunch of Kas, Kbs, polyprotic acids, things like that. So for the homework, when you were doing the polyprotic acid, basically all you do is you only do the first Ka of any polyprotic acid because the two corresponding ones are always much, much weaker. Okay? That makes sense? So, do we have any question on how to do this? So let's compare what would have happened if we just added 0.01 moles of sodium hydroxide to 1 liter of water. How would we calculate this? Anyone know? Honey, how would we calculate the pH if we have 1 liter of water and we add 0.01 moles? 0.01 moles of NaOH added to 1 liter of water. Do we know the molarity of this solution? What is it? It's just 0.01 molar. If we know that it's 0.01 molar in OH minus, can we calculate the pH of this solution? How do we do that, Molly? So this is a strong base. How do we calculate the pH of a strong base solution? Any thoughts? Sophia? You will, but first, before you do that, what do you have to do? So no, we have the molarity. The pH equals, so this is the OH minus concentration. Can we find the pOH of this? All we do is we take the negative log of this. What does that give us? 2. That is the pOH. 14 minus 2 gives us 12 for the pH. So in this solution that started at pH 7 and went up to pH 12 after 0.01 moles of NaOH, how much did the pH increase in this case, Ian? It went from 7 to 12. How much did it increase? 5. In that last problem, we added 0.01 moles of NaOH to a buffered system. It went from 4.74 to 4.83. How much did that increase, Janessa? 4.83. It went up to from 4.74. 0.09. So in a buffer, the same addition increases the pH by 0.09. In water, the same addition increases the pH by 5. Are we noticing a difference? What would happen if our blood was not buffered? Probably, right? We would learn how to buffer our blood, okay? Because everyone would just die if not, okay? So that's how we do that. Real quick conceptual check. A buffer contains equal amounts of weak acid and its conjugate base, and it has a pH of 5.25. What would be a reasonable value of buffer pH after the addition of a small amount of acid? Okay, Amanda, what do you think? We have an initial pH of 5.25 of a buffer, and we're going to add acid. Do you think the pH should go up or down with the addition of acid, Amanda? Very good. So we can eliminate 5.35 and 6.35, right? You see how I take a multiple choice problem and I start eliminating the obvious wrong answers? Okay. Now, since it's a buffered system, Amanda, would it only go down a tiny bit or would it go down kind of a lot? Very good. It would only go down a little bit. So we would, I mean, I just showed you, we're not putting any numbers in this. If our two options are changed by over 1 or 0.1, we're going to choose a smaller amount. The answer should therefore be B. Since acid is added to the buffer, the pH will slightly lower. Therefore, answer A reflects too large of a pH change, even though it's going in the correct direction. C and D are in the wrong direction, leaving us only with B. And that's how we would do that. Okay. So with the basic buffers, I just talked about this. A basic buffer is exactly the same, right? If a buffer, this is the weak base. Okay, so this is a weak base generically. When we react it with water, it pulls a proton off to make BH plus. This is the conjugate acid of the weak base. And notice how the reason why it's a base and the reason why pH goes up is because we liberate hydroxide from the water, which was acting as the acid in this situation, right? The water added its proton, leaving an OH minus. That's why adding that's why the base is a base. Okay. Same thing happens if we add acid to this. What's it gonna? So now we have a buffer system containing this and this. This is the buffer. H plus will react with that to give more of that. If we add OH minus, the OH minus will pull off one of those protons. So this is NH4 plus. The OH minus will grab off one of these protons, making water and NH3. So the same exact concept is true. It's just a different thing in there. So a buffered system consists of a weak base and a conjugate acid, or a weak acid and its conjugate base. Does everybody see that? Why can't we use a strong acid and its conjugate base, Kayla? Because the conjugate base of a strong acid has no desire to pick up a proton because it completely ionizes. So when we would add acid, the Cl minus is like, I don't want that. I was just with a bunch of strong acid and I let it go. You're allowed to let things go in life, okay? That's not chemistry. That's in real life. So in this case, there's also a version of the Henderson-Hasselbalch that works for bases. What do we notice about this Henderson-Hasselbalch for bases? What are we noticing about this, Ricardo? It looks pretty much like the same thing, right? The Henderson-Hasselbalch normal is pH equals pKa plus the log of base over acid in green, right? That's the normal one. That's the one we're going to use most of the time. But if we want to use the one for the bases, notice that we have POH, that's the opposite of pH. PKB, that's the opposite of pKa. How is the log is the same? What is BH plus in comparison to B? The acid is on the top and the base is on the bottom. So when we use the POH formula, you put the acid on the top and the base on the bottom. Everybody see this? So you do the same things you were going to do, you just flip it a little bit. Everybody comfortable with that? So let's calculate so basically, what do you think happens if we made a buffer with equal concentrations of, so in this case, what are we doing? 0.5 molar and 0.2 molar. Going back to this equation, what happens if we have equal concentration of conjugate acid and the weak base? What do you think is going to happen in this situation? What is the POH going to equal, Jack? The PKB. Okay. So the same concepts that we saw in the acid hold true. To use this equation, if this is saying use the Henderson-Hasselbalch to calculate the pH of a buffer that is 0.5 molar NH3 and 0.2 molar NH4Cl. So this is NH4Cl. Why is it NH4Cl? NH3, what is the conjugate acid of NH3, honey? So after NH3, which is a weak base, picks up a proton, what is its formula? NH4 plus. So the actual conjugate acid is NH4 plus. Why is this saying NH4Cl, Jessica? So that's the conjugate acid of the weak base, but we couldn't just add NH4 plus. You can't add an ion. You have to add it as a neutral species. So we just pop on. So just like with NaOH, that we have to add the Na to the OH minus, right? In this case, we can't just add NH4 plus. We have to put, and what is Cl? Cl minus. The Cl minus neutralizes the NH4 plus to give us that NH4Cl over there. Okay. So ignore the Cl minus, and whatever's left is your conjugate acid. Ignore, just like when you see sodium, ignore the sodium plus and whatever the other thing is. Okay. So that's how we solve for that. You could also try this using the form of the Henderson-Hasselbalch with POH and then try and solve for pH. Let's try and compare that. So in this case, so for this problem here, they gave you the PKB of the what is it? PKB has to be for NH3. You could look up this PKB value in the table that I gave you at the end of chapter 15. What they did here is they used the actual form of the Henderson-Hasselbalch equation. So that form involves pKa. Is pKa the same as pKb? They're not, but they're related, right? How are they related? pKa plus pKb equals 14. So if we wanted to find the pKa of that conjugate acid, it is 14 minus the pKb. That's where we get 9.25. We plug that in for pKa. We make sure to put the base concentration, which was the 0.5, and the 0.2, which was the acid there, and we get a pH of 9.65. Let's see if it's easier to use the POH Henderson-Hasselbalch equation. In this case, the PKP, let me change color here. Let's make this red. In this case, so this is the formula, right? This is the POH Henderson-Hasselbalch. We can directly use the 4.75. Now we have to realize that I'm using the 0.2 on the top and the 0.5 on the bottom because the 0.2 is the acid and NH4Cl is the acid, and the 0.5 is the base. So I do log of 0.2 over 0.5. That gives me 4.75 minus 0.391. That gives me 4.35. I do 14 minus that because that was a POH. I want a pH. We get 9.65. Are those two values equal? Which one's easier to use, Bryce? They're both pretty easy, but one of them you have to do a little bit more. I guess they're the same amount of steps, right? So it's just whatever you're more comfortable with doing. Okay. You just have to make sure you have these things written out correctly. Do we know how to use all these things? Yes? Good. Okay. Let's talk about buffer effectiveness. Okay. Let's talk about it like this. Okay. Let's say we actually had more than 20 people in class. So we had our 50 and 50, 50 weak acids, 50 weak bases. If every time somebody came in, if it was like a acid, we would have to send our conjugate base to neutralize that, right? If we have 50 and 50 in a normal class day, or if we have like today, 5 and 5, it's getting way more than 5, but people on Zoom don't know, people on the recording don't know. But if we only had 5 weak acids and 5 weak base, which would be the more effective buffer elution? Which one could negate more added acid? When you have 50 and 50 of the acid and base, or 5 and 5 of the acid and base? And why is that? Because you got more in there. So in general, a good base should be able to neutralize moderate amounts of acid and base. However, there's a limit. If we have 50 and 50, we could theoretically take on 50 acids that came in or 50 bases. If we only had 5 and 5, how many could we take on, Bailey? Of either one? 5. So which is the more effective base? The one with high concentrations of each or low concentrations of each? The higher, right? So in lab this week, there was something called when you make a buffer, if you add the two concentrations, that equals the total, what was it called? Who was in my lab? Remember we had to make it add up to 0.1? What was that called? It was a 0.1 molar total buffer or something like that. Whenever you have a buffer, if this is the buffer with 0.5 molar and 0.2 molar, that's a buffer. Everyone agree with that because it has conjugate acid and conjugate base. The total buffer, I forget what the word was. Anyone remember what it was called? Anyway, you add them up and we would say this is a 0.7 molar buffer because you added up the 0.5 and the 0.2. In lab, we wanted it to be a 0.1 molar buffer. So we figured out what the ratio was, but they didn't add up to 0.1. So we had to do some math to get it down to that number, right? That's just helping you out, those of you who have lab on Friday, or those of you who just do lab and then bounce out and don't do any calculations. Now you know how to do that. So there's a limit. We call this limit the buffering capacity. When we have 50 and 50, we have a buffering capacity of 50. When we have 10 and 10, we have a buffering capacity of 10. If we had 1,000 and 1,000, we'd have a buffering capacity of 1,000. Everyone comfortable with that? Okay. So if we have a concentrated buffer versus a dilute buffer, a concentrated buffer can neutralize more acid than a dilute buffer. That should make total sense. So that's called the buffering capacity. The buffering range is the pH range that a buffer can be effective. Okay. In general, you can calculate it. It depends on two factors, the relative amounts of acids and bases and the absolute concentrations. The most effective buffer will be when the base to acid ratio is 1, because you can take on, like if we have 100 and 100 and we're equal, we could take on 100 acids or 100 bases, right? We have a good effective buffer. Are we still a buffer if we have 150? We still are a buffer, right? We could take on 100 of whatever the hundreds are, but we can now only take on 50 of what the other one is. So we'd have it be a slightly less effective buffer. So to make this ratio stay as close to 1, that's when we were looking at an effective buffer will be when the base to acid ratio is between 0.1 and 10. So you shouldn't have more than 10 times the amount of one over the other. A buffer will be most effective when it's at that 1-to-1 ratio. But if you have a 0.1-to-1 ratio or a 10-to-1 ratio, it's still pretty decent. Once you have more than 10 times of the other thing, it's a kind of a crappy buffer, though it could still be effective if you know you're only adding the thing that you have more of. Okay? So in general, when you're choosing a buffer system, if you have a bunch of different combinations of weak acid and conjugate base, the pH you want your buffer to be, you should always choose the buffering system that has a pKa within 1 unit of the pH you're desiring. So in lab, I think we had like a 2.3 was 1 pKa. I think it was like a 7.4 maybe, and like a 10.2. That means that if you chose this buffer, it should be between 1.3 and 3.3 should be the buffer pH that you want to make. This one should only be between 6.4 and 8.4 within 0.1 of either side. And this one should be between 9.2 and 11.2. Okay? So if you have a bunch of options, so like if you're trying to make a buffer that is a pH of 8.7, neither of these would be that good. What do you think you would want? What type of system would you want to use in this case? Robert? So, I mean, I'm saying that both of these, so are these the only three, the ones we had in lab, are those the only three weak acid and conjugate base systems in the world? So what would you probably want to try and do? You'd want to find a different acid that has a pKa around 8.7, right? So you would look at the different weak acids that are available, find one with a pKa closest to 8.7, and that would be the combination you would want to use to make a buffer at that pH range. Does that make sense? Yeah. So, I mean, if you only had these three, then obviously you would have to choose the one that's the closest. But if you had a list of every weak acid available, you want to choose one with a pKa closest to the pH you're making, and that will thereby make it so that it'll have a pretty close ratio to 1-to-1, and it will be both a effective buffer and what's the other word? It'll have a good buffering capacity and a good buffering range. Okay. So, and this is just a way to show you when we have equal, so this is just showing you when you have equal concentration of weak acid and its conjugate base here, 0.1 and 0.1, when we change the pH only changes by 1.8%. We could use the exact same buffering system, but now if we use 0.18 molar and 0.02 molar, it's still within that 10-to-1 ratio, so it's still a semi-effective buffer. But notice that when we add something, the pH changed by 5%. So because those ratios were pretty far in the beginning, far apart, it does not help stabilize the pH as much. Having the concentrations closer together will always cause the pH change to be more minimal. Does that make sense? And that's just the way you have to think of it. Okay. So we've said that. So this is just talking about what I said. So this is where it says you want your pKa less than or greater than 1 of the pH range you're trying to do. Okay. So this is just taking those effective ranges, plugging into the Henderson-Hasselbalch. And when I told you it should be within 1 unit. So if your desired pH is 7.4, you want to choose a buffer system that has a pKa between 6.4 and 8.4, right? The closest to 7.4, the better. If you want one that's a pH of 13, you'd want to choose a pKa that's between 12 and 14. Okay, so this just helps us decide which buffer system we want to use. Yes. I think it was just saying of those three, choose the one that it's supposed to be. I mean, I don't know who's your lab teacher. So I think did he upload a Canvas like submission sheet? So that's the one I made. So I made it to where you're only gonna choose between the H3PO4, H2PO4, HPO4, or PO4 3 minus, right? So I mean, maybe if it's an open-ended question, they might not be within one, so then you could go look up PKs, but I was trying to make it as simple as possible. Of those four different options, choose the one that's closest. Well, in lab, you're always gonna have error, okay? So that goes without saying. A, our pH meter sucks. B, you guys are all doing the experiment. Just kidding. But I mean, like realistically, you're doing it one time. You're not like doing it in replications. If we did it like 10 times, you would get the hang of it and you'd probably get a lot better at it. Anytime you do anything once, it's not going to be great, right? Anytime someone's like, oh, let's learn this new sport, pickleball, are you going to be an expert on the first day? But if you play for 5 months, you're going to be pretty good. Yeah, you'll be expert. It's so easy. It's just, not just kidding. I want a dog pickleball. I'm gonna start playing that once I get super old. Um, when choosing an acid to make a buffer, choose one with pKs closest to the pH of the buffer. Okay. So if I wanted to choose if I wanted to make a buffer with a pH of 4.25, which of these four acids and their conjugate base would be the most ideal in this situation? What do you think, Scarlett? So what do you think we would want to do? If I told you you have to choose one of these, or else you do not get the take-home exam, would you choose one of them? And if I told you, based on what we've said the last 15 minutes, you can think about it. So what have we been saying, Ricardo? Help her out. Which of those four values do you want to get? The one that's farthest away or the one that's closest to it? Okay, so Scarlett, go ahead, Ricardo. We definitely cancel out the 7.54. Very good. We can cancel out the 1.95. Good. So which of those two is closer to 4.25, Scarlett? Everybody agree with that? We would use a formic acid, HCHO2, and its conjugate base, which would be CHO2 minus. Can we add CHO2 minus, Angelina? So how would you add this CHO2 minus? No, it already has an H on the weak acid. Jessica? Sodium CHO2 or Na plus. This thing is that thing. Okay. So when you're getting confused why these things have sodiums, the reason why is you can't just add that negative thing. Okay. So that would be that one. I don't know what that is. The best choice would definitely be the 3.741. Okay. What did they say? Oh, yeah. So they did put 3.74 here. So they chose the 3.741. That value was kind of close to that. So I was a little worried. But if you use this one, it would be even a bigger ratio, more spread out than the 3.24. So that's the ratio of base to acid. Okay. So real quickly, I think we should be able to finish this chapter. Buffering capacity is the amount of acid or base that can be added to a buffer without causing a large change in pH. The buffering capacity increases with increasing absolute concentrations, just meaning 1 molar is better than 0.5, which is better than 0.1, which is better than 0.01. That's what this statement is saying. And then buffers that need to, and then as that ratio approaches 1, it makes it better. So you want to make sure you choose. And there are some caveats to this. Like I said, if you know you're only adding acid, like you're not going to have to add any base, then maybe you would want to have a bigger ratio of bases, right? So if we had 50-50, that's good for negating both things coming in. But if we know we only have acids coming in, we don't really need to have that much acid in there. We would just want to have a lot of that conjugate base in there, right? So don't say like it's not absolute as with anything. Nothing is absolute, but that's the way it works out. Last slide of chapter 16. Oh, no, it's not. Last slide of this PowerPoint. So starting on Monday, that is the meat of potatoes of this take-home exam, okay? I'll probably pass out the take-home exam maybe at the end of the week or something like that. Maybe give you a whole weekend. Or would you rather just have like 5 hours for it? Donatella? What do you choose? Yes, you can. What do you choose? And if you choose wrong, everyone's going to hate you. So what are you going to choose? Okay, Bryce, choose for the class. Do you want a weekend or do you want to have a set amount of like 5 hours? I mean, we might not even be done by Friday, so then maybe I'll give it to you on Monday and give you till the end of the week, Friday or something. But I'm gonna give you a few days, okay? Why? No one wants to do stuff on the weekend? Give you the summer? Okay, then that means no one gets their grades. All right, you all have a wonderful weekend. We are starting, so listen to this weird concept, okay? On Monday, we are gonna be starting 16B. Let me get this thing off. We are going to be starting 16B, okay? If you wanted to, could you look at these slides before I teach it to you, and now you're seeing it for the second time? Probably not. If I was in this class, would I do it? Guaranteed not. But I also come to class, and everything I listened to in class, I learned, okay? I remembered what the teacher said from Monday, from 2 months ago. I come to class and I listen. I miss like less than 3% of my classes in all of college. And when I was in class, I usually listened. There were sometimes I didn't because I was sleeping. But other than then, I promise you, when you come to class, you're all doing the big step of coming. That's great. Pay attention when you're here, okay? 1 hour of listening here is like 5 hours of trying to do it on your own. So you're saying like, oh, I got busy plans this weekend. It's Easter. I got to go have fun. Well, then listen in class for that hour and it'll make your weekends better. Have a wonderful weekend. Aloha, everyone. Turn in your test corrections if you have any. Too late, class.